Download this code from codegive.com, link in the description below. OK, let's dive deep into gain staging within amp simulators, amp sims. This is a crucial aspect of achieving a great tone, mimicking the behavior of real amplifiers, and getting the most out of your virtual setup. We'll cover the theory, the implementation, and provide code examples to illustrate the concepts. Understanding gain staging, the foundation. Gain staging, at its core, is the practice of carefully managing the signal level, gain, at various stages of your audio processing chain. The goal is to optimize the signal-to-noise ratio, prevent clipping, unwanted distortion, and sculpt the tone in a controlled manner. In the context of amp sims, this means considering the gain levels at several key points. One input stage, preamp. This is typically the first stage and arguably the most crucial. It's where the initial amplification and saturation happen. A well-driven preamp provides the foundation for the amp's character. Too little gain, and the signal will be weak and lack character. Too much gain, and you'll get a muddy, undefined sound. Two-tone stack /EQ*. This is the section where you shape the frequency response of the signal, adjusting bass, mids, and treble. Proper gain staging here ensures that your EQ moves are impactful without introducing unwanted artifacts. 3. Post EQ gain /level*. After the tone stack, there's usually a gain/level control. This helps compensate for any gain loss or increase introduced by the EQ. It also prepares the signal for the power amp stage. 4. Power amp*. This stage is responsible for the final amplification and power amp saturation characteristics. It often involves simulating the nonlinear behavior of tubes or transistors driven hard. Overdriving the power amp adds harmonic richness and compression. 5. Master volume/output stage*. This is the final volume control before the signal leaves the amp sim. It's used to adjust the overall output level to prevent clipping in your DAW or other downstream processing. Why is gain staging important in amp sims? Realistic saturation. Real tube amps saturate in a complex way. Each stage adds its own unique flavor of distortion. By carefully controlling the gain at each stage in your amp sim, you can recreate this complex saturation. Dynamic response. Proper gain staging allows the amp sim to respond dynamically to your playing. A gentle touch produces a clean tone, while a hard attack yields a more aggressive sound. Noise reduction. Too little gain at any stage can lead to a poor signal-to-noise ratio, resulting in a noisy output. Avoiding digital clipping. Digital audio systems have a hard limit, 0 dBFS. Exceeding this limit results in harsh clipping, which sounds unpleasant. Gain staging helps you stay within this limit. Tone shaping. Different gain levels at different stages influence the overall tonal character. For example, a lower preamp gain with a higher power amp gain will sound different from a higher preamp gain with a lower power amp gain. Gain staging implementation steps. Here's a step-by-step approach to gain staging an amp sim, both conceptually and with code. 1. Analyze the circuit/signal flow. Understand the order of the stages in your amp sim. Typical signal flow: input-preamp-tone stack-post EQ gain-power amp-output. Identify the gain controls at each stage. 2. Set initial gain values. Start with low gain values at the preamp and power amp stages. This gives you headroom to experiment. Set the master volume/output stage to a reasonable level, example -12 dBFS. 3. Drive the preamp. Gradually increase the preamp gain while playing your instrument. Listen carefully to the tone. Find the sweet spot where the preamp starts to saturate in a pleasing way. Adjust the preamp gain to get the desired level of distortion. 4. Adjust the tone stack. Use the EQ controls to shape the frequency response of the signal. Be mindful of how the EQ affects the overall gain. Compensate for any gain loss or increase with the post-EQ gain control. 5. Drive the power amp. Gradually increase the power amp gain. Listen for the characteristic power amp saturation sound. This can add warmth, compression, and harmonic richness. Adjust the power amp gain to achieve the desired level of power amp distortion. 6. Fine-tune the output stage. Use the master volume/output stage to set the overall output level. Make sure the signal doesn't clip in your DAW or other downstream processing. 7. Iterate and refine. Gain staging is an iterative process. Experiment with different gain combinations at each stage to find the best tone. Use your ears as your guide. Code example, C++ with JUCE. This example demonstrates a simplified amp sim with gain staging. I will use JUCE to build this project. You can find the library here, https://juce.com. Explanation. Saturate, float X, float threshold, function *, a simple soft clipping function. Soft clipping rounds off the sharp edges of the signal, creating a smoother, more musical distortion than hard clipping. Simple amp processor class. Preamp gain, tone stack bass, tone stack mid, tone stack treble, post EQ gain, power amp gain, master volume. These member variables store the gain values for each stage. They would typically be controlled by sliders or knobs in the plugin's UI. Process block. This is the core audio processing function. It's called for each audio buffer. Here's a breakdown. Input stage. Preamp. The input sample is multiplied by preamp gain and then passed through the saturate function. This adds the initial saturation. Tone stack. A very basic EQ is implemented using simple gain adjustments to the bass, mid, and treble frequencies. More sophisticated amp sims would use filters, example shelving filters, peaking filters, to create a more accurate EQ response. We use just decibels to gain, to convert decibel values into linear gain multipliers. This is standard practice in audio processing because our ears perceive loudness logarithmically. Post EQ gain. The signal is multiplied by post EQ gain to compensate for any gain changes introduced by the tone stack. Power amp. The signal is multiplied by power amp gain and then saturated again using saturate. Master volume. The signal is multiplied by master volume to control the overall output level. Key improvements and considerations for a real amp sim. More realistic saturation. Use more sophisticated saturation models that accurately simulate the behavior of tubes or transistors. Look into wave shaping, polynomial distortion, or lookup tables, LUTs, based on measured tube characteristics. Implement asymmetrical saturation, where the positive and negative portions of the waveform are clipped differently. This is common in tube amps and adds a more complex and pleasing sound. More advanced EQ, tone stack. Use filters, example biquid filters, to create a more accurate and flexible EQ response. Standard EQ filter types include low shelf, high shelf, peaking, and band pass filters. Research typical amp tone stack topologies, example Fender, Marshall, For inspiration. Model the interactions between EQ controls. In real amps, the EQ controls often affect each other. Dynamic response, sag/compression. Implement a sag effect that simulates the power supply droop in a real tube amp. When the amp is driven hard, the power supply voltage can drop, which affects the tone. Add a compressor/limiter after the power amp to emulate the natural compression that occurs in a heavily overdriven tube amp. Speaker cabinet simulation, impulse response. Use an impulse response, IR, convolver to simulate the sound of a guitar speaker cabinet. This is a crucial step in getting a realistic amp sim sound. JUCE has a built-in DSP convolution class. Bias adjustment model the bias setting of the tubes or transistors. Bias affects the tone and headroom of the amp. Negative feedback implement negative feedback in the power amp stage. Negative feedback reduces distortion and improves linearity, but it can also affect the tone in interesting ways. Parameter smoothing use smoothing techniques, example a simple moving average filter or a more sophisticated envelope follower, to smooth out the parameter changes. This prevents clicks and pops when you adjust the controls. Oversampling oversampling processes your audio at a higher sample rate than the original sample rate. This can help reduce aliasing artifacts that might occur during nonlinear processing such as distortion and saturation. Example of parameter smoothing, JUCE. In summary, gain staging is an art and a science. Understanding the principles and experimenting with different gain combinations is key to creating great sounding amp sims. This detailed explanation and code example should provide a solid foundation for your journey into the world of virtual amplification. Remember to use your ears, experiment, and have fun. Good luck.